The next topic for atomic theory has to do with something called the subatomic particles. And you've already been hearing about the subatomic particles a lot. They include the three main particles that are sub or below, or we'll say smaller than an atom, so therefore subatomic, smaller than an atom particles. Remember that Dalton thought that the atom was the smallest particle, as did a lot of people of his day and before him. But we now know that there are still smaller particles within the atom that can contribute to the mass and the behavior of the atom of each element. And those particles are the subatomic particles. Now we're going to talk about the three main subatomic particles. But you'll know if you look a little further on your own, and this won't be part of class necessarily, but if you look further, there are actually still smaller particles that make up each of those. So there are particles that make up the subatomic particles, subatomic particles. They're a crazy small piece that perhaps are not even the smallest yet. But we won't be talking about those. Those are a bit more for something that you might study if you take a college class in, say, physical chemistry, or look further into the nuclear physics side of what makes atoms work. So we're going to look at subatomic particles at the level of the protons, neutrons, and electrons, the three that are kind of the most common. What I want to put up here first for you is a sort of just a quick snapshot summary of what we talked about so far. And those are the three subatomic particles and their sort of order of discovery. You can look here that the electron, then the proton, then the neutron were discovered in that order. The electron in 1897 by Thomson and company, the proton in 1917 by Rutherford, and the neutron in 1932 by Chadwick. Now that's a pretty short window. It's a 35-year window. We went from knowing that there were for sure no subatomic particles, although people thought as early as probably the early 1800s for sure that there was certainly subatomic-sized particles or something that was behaving like that. We went from not knowing them for sure to knowing all three of them in 35 years. That's a blink. That's shorter than my lifetime. And so not a lot of time at all to go from knowing very little to knowing a whole heck of a lot. This is a very, very important window of time in the history of chemistry and understanding how the atom works, which really is the backbone to chemistry. So these 35 years are sort of the golden age of really getting chemistry figured out. And they happened here within the last 100 years or so. So it's a very, very recent convention to have subatomic particles and to really know about them to the degree that we do. We'll find as we talk more about things that there hasn't been a whole lot of huge change in our understanding of the atom since then, but there are very fine changes that we do understand better now that make a big difference in something called quantum theory and so on as we go. But important to know, and this is just a review slide, that all three of these happen within a short window of time, that the electron, then the proton, then finally the neutron were discovered in that order, and that all three of these teams and discoverers happened to work at the same place, which was a place called the University of Cambridge in England, specifically the Cavendish Laboratory in a couple of their cases. And that's what you see in the picture here, the entrance to the Cavendish Laboratories at the University of Cambridge in England. Pretty famous place. If you ever get a chance to go to England and visit Cambridge, I'd highly encourage you to stop by and see this place. There's now a museum there that you can visit, and it would be kind of like visiting the cradle of chemistry in its infancy. A pretty amazing place on my bucket list, although not terribly high. So a subatomic particle is sort of a snapshot table here. I want you to make one like this in your notes with these 5 columns you see across the top. Subatomic particle, the symbol, the mass, the charge, and the location of those particles. We're going to kind of summarize this in a nutshell here, and I'd like you to put down all three of the subatomic particles along with their information as this table will fill in here. So the proton is our first one in no particular order here necessarily. The proton is abbreviated as a P with a plus. That's a lowercase p, and all the symbols will be lowercase letters. Lowercase p with a positive sign. It has a mass of what we call 1 AMU. Now that's not a mass unit that we're used to. AMU stands for the atomic mass unit, very generic sounding mass unit, and it is. But it's the unit that we use to record and describe the mass of subatomic particles like the proton, the neutron and electron, and also the mass of an atom, a single atom, usually described in terms of AMUs, at least in the way that we'll use it. We can also use grams. We'll talk more about the mass of protons and an AMU and electrons and atoms in grams as we go further into the year, but for now a convenient way of measuring the mass is the AMU, the atomic mass unit. So the proton has a mass of 1 AMU. We'll talk more about how the AMU was described and defined later. The charge of a proton is 1 positive or 1 plus, and the proton is located, as we know now, in the nucleus of the atom, as we sort of discovered or figured out with the Rutherford model of the atom. The second subatomic particle I'll tell you about in this table is the neutron. And the neutron, again, is a lowercase n for neutron with a 0 to show that it's neutral and has no overall charge. It also has a mass of 1 AMU, so its mass is essentially the same as that of the proton. If we were to use a bit more precision and measure these in mass with grams, we'd find that their masses are slightly different, but not so much that they show up in AMUs. So a good example of significant figures in action. The mass of a neutron, right around the same as the mass of a proton. In fact, the neutron trivially is just slightly greater than that of a proton. Its charge is 0, no charge at all, and its nucleus location, just like the proton, means that all the heavy particles, including the proton and the neutron, are there in the nucleus, and all the mass, therefore, sort of concentrated in that tiny pinpoint in the center of the atom. An electron has a symbol of E, lowercase e for electron, -1 or minus, and so E minus for an electron. The mass of an electron is listed officially as 0 AMUs. We say electrons have no mass. In actuality, they do have mass, but in another example of significant figures, when something's mass is so small that it would almost be sort of indescribable or not considerable, essentially, that it has a mass of 0 AMUs, we're looking at a mass that's actually 1 over 1/1840th the mass of an AMU. And when we consider it as that small, its mass is inconsequential. It'd be 0.00 something in terms of AMUs, and it's not really worth considering in terms of the mass of an atom. It's the protons and the neutrons that give the mass of the atom its being. The mass of an electron, I always kind of consider, is sort of like sticking stick a sticker off of a banana and stick it onto a bowling ball. You don't feel that difference in mass. You don't feel that change. And so overall, we would consider that sticker would really have no mass at all. Compared to the protons and the neutrons, the electrons are so very light. And the charge of an electron at -1 cancels out the charge of the proton in the atom. So in a neutral atom where the charge overall is balanced, the protons and electrons are equal to each other. And electrons, for now, we'll simply say are located in the electron cloud. The electron cloud is a very vague term that we'll use for now and stick with. Later on, we'll get more into detail about electrons and their behaviors and their movements within that electron cloud, and really where they're at and how they're moving. It's a little more, in fact, a lot more precise than to simply say electron cloud as if it's some sort of fuzzy cotton candy blur. That's as far as we knew about it at the time of, say, Rutherford, but Bohr made it more precise, and as we'll talk about later on, a fellow by the name of Schrödinger and his team later into the early 1900s made our vision even different. So that's our preview of subatomic particles and sort of a summary of what we know about them as far as their order of discovery and who found them, and a little bit of organization about subatomic particles and how and where they exist in the atom in general. Some of their behaviors and things are based off of what's on this table, so it's important to have in your notes sort of as a good summary spot to go back to as we go further and start looking at the periodic table.